So it's a pleasure to welcome today's speaker, Dr. Althea Wilkinson. She graduated in natural sciences, that's physics, from Cambridge, and subsequently went on to do a PhD in radio astronomy in Manchester. After time spent in California, she was back to Manchester again, worked at Jodrell Bank, and is presently a domain specialist in the Square Kilometre Array Signal and Data Transport Consortium. I got all those words right, I think. It's a pleasure to welcome you today, and Althea is going to speak to us on the Square Kilometre Array Telescope, Engineering to Reveal Cosmic Origins.
Thank you very much, and thank you for coming today to listen. Right. Well, what do we think about when we're thinking about the universe? How do we go about it? This is a gorgeous picture, as might have greeted the people of the ancient Near East some 4,000 years ago. It's taken from Iran. As you can tell, it's the Milky Way, our galaxy, and it's taken by a wonderful photographer called Babak Tafreshi. I recommend his work. These are, we're asking questions that have been current for all time. What's out there? How and what's it like? Why is there anything at all? Interesting. And most critical to us, how do we fit in? I always look at science as working within what exists, so within what has been created or is there. And faith, by definition, is by revelation, to individuals and by the word. So the question I want to come to eventually today is, how do these two fit together? But first of all, I'm coming by the way of the Square Kilometre Array Telescope. The sort of cosmology that the ancient Near East might have had 4,000 years ago is depicted by this cartoon. I mean, it's obvious when you go out and look up, it's a nice blue bowl, isn't it? So, of course, it's a bowl. We know that there are waters above the bowl, unfortunately. We've had rather a lot of them recently. And the stars and the moon are all stuck around the inside. But the main thing about that is it's hugely anthropocentric. You know, we are at the centre, the world was created for us, and all the rest of it. How do we see it now? Well, a little bit differently. We've never been out there, but that's taken by the Cassini mission as it went under the rings of Saturn. So that's looking back at the Earth, which is indicated by that arrow, and yeah, it doesn't look very anthropocentric universe so much, does it? I always find that a very, very sobering picture. Everything that's alive that we currently know about in the universe, and I stress currently, is contained on that dot. It may change soon if we get evidence of life on other planets. But at the moment, that's what there is. Okay, well, what insights do we get from science? That's what we can get from the naked eye and pictures. For a long time, 400 years rather than 4,000, for a long time, assisted views of the universe, once we could go beyond our naked eye, were limited to this tiny, tiny fraction which you see there, the optical spectrum, what we can see with our eyes. But of course, the electromagnetic spectrum extends a lot further than that. It extends to much longer wavelengths, to the infrared and radio waves, and the radio regime is what I'll be talking about mainly today. But it also goes the other way to much shorter wavelengths, and X-rays and gamma rays. So we now have astronomy over this whole range of wavelengths, and we have other things to help us as well. We expect astronomy to be done with things that look pretty much like that. That's an artist's study of the European Extremely Large Telescope, which is being built in Chile. That's a big optical telescope. We also have, or we will have, things like that, space telescopes. This is the successor to the Hubble telescope. This is the James Webb Space Telescope, which is going up very shortly, and you know, will be a wonderful asset. But in the radio wavelength, this is our biggest telescope now on Earth. This is the 500-meter aperture spherical array, or FAST, built by the Chinese in a bowl in the mountains. It is, as they say, it is half a kilometre across. It is an extraordinary sight. It really is huge, and a terrific credit to the technological skills of the Chinese. It can't, of course, move because it's held in the bowl of the hills, but the centre part can be deformed into a parabola to point it. Very, very clever technology. We are not likely to build telescopes any bigger than this. It's too expensive, gravity's winning, and it's just too much of an engineering challenge. But we want big telescopes. We've got very tiny signals to see. We want big telescopes. What we have, on the whole, what we're interested in seeing in space is hydrogen. The reason for this is that that's the commonest element in the universe, and the transition that we're interested in, if you have a somewhat excited hydrogen atom, been near a star or something, and both the spin of the proton and the spin of the electron are pointing in the same direction, about every 10 million years, it will undergo a transition to a more stable state, and the electron spin will go anti-parallel to the proton spin, and it will emit radiation of wavelength 21 centimetres, about that long. And we are very interested in seeing this. I said it only happens once every 10 million years, but fortunately there is an awful lot of hydrogen out there, so we do actually get a measurable signal. But it is very faint. The reason we want to see it is because you learn so much more. This sort of yellowy bit is the optical, what you can see in optical wavelengths. This purpley bit is the extra information you get from looking at the hydrogen surrounding that galaxy. And you can see there's a lot more of it than we could see in the optical radiation. So we want to be able to look at all wavelength ranges. But particularly this wavelength there, that is a radio wavelength, and we're particularly interested in that one. So what we want is an area about 200 times the area of that telescope, which is the Lovell telescope, which is the biggest one we've got in England, or even 13 times that of FAST. So we just need something really, really big. A really big photon bucket, really. We're talking here about sensitivity. And we really need the biggest collecting area we can get. So how do we go about building bigger telescopes? And I acknowledge my debt here to one of our Cambridge colleagues, Malcolm Longair. He's got a very nice way of showing this. Well, radio telescopes reflect signals from distant objects to the focus of a parabolic dish, which I'm not actually seeing the dish. You can just about see the dish. Sorry, that's very faint. There's a parabolic dish there, which you can just about see. But the point is that they're reflecting parallel wavelengths from distant objects to the focus. But the point is you don't need the whole dish. You can make do with a partially filled dish. If you have those two little light bits there, the reflecting surfaces are part of the parabola, but they don't have to be the same dish. If you cover up most of the mirror, you still get the radiation coming and meeting at the centre in phase, combined correctly if you adjust the path lengths so that that's exactly what happens. And so once we know that electronics and fibre costs, so digital electronics and fibre costs becoming much, much cheaper, it is much cheaper and easier to build large collecting areas out of lots of small ones, lots of smaller elements. So this is what we are aiming to do, is to build arrays of lots of smaller receptors and do the clever stuff with electronics rather than bent metal. So this leads us to the idea behind the square kilometre array. That's an artist's impression. It's not built yet, but lots of little telescopes are equal to one big dish. And that's the idea of where we're going. Now, this project has been going for about, getting on for 40 years, actually. It first started. I've been connected with it for a very long time. And I'll talk a little bit about the thoughts I have on that later. But first of all, let's look how we decided where to put it. We're not putting it in this country. As you can tell from the background there, that doesn't look much like England. How did we choose the sites? Well, I showed you that picture before with the 21 centimetre wavelength. But of course, a lot of that hydrogen is very redshifted because it's coming to us from very distant points in the universe, the emission. So, as we go on, it gets shifted to longer and longer and longer wavelengths, and these go through the mobile phone region, the aircraft region, digital TV, and FM radio. Interference all the way along. We need places where the digital interference is really, really low, preferably none, but I don't think that exists in the world anymore. The things that worry us are mobile phones, laptops, PCs, electric fences, you know, anything that's giving off that sort of a signal. So that was what was behind the thinking when we sort of started looking for sites. This is a map of interference, or the digital emission in that frequency around the world. And you can see the Northern Hemisphere is not ever such a good place to think about putting telescopes. And we've got lots in the Northern Hemisphere already. We didn't really need extra ones in the Northern Hemisphere. And the Southern Hemisphere is special because you can see the galactic centre better from there. So we were looking at the Southern Hemisphere. A competition was run for southern sites. Unfortunately, we can't put it in the ocean, rather technically tricky. So you can see that there's a good reason for using Western Australia. Green is good. There looked at sites in South America, but none of them were too useful. The Democratic Republic of the Congo is perhaps not a very good idea. So we've ended up in the western part of South Africa. And a political decision, it was all going to be on one site, there was a political decision made to put it in two sites, basically because the two sites had built precursor telescopes and they worked so hard and put so much into it, they both deserved a reward. So they both got a reward, essentially. So that's where it's going to go. So in the Karoo, this is the Karoo Desert in South Africa. That's going to get the higher frequency telescopes called the mid-array, and sort of inland and north from Perth, which is going to get the low frequency telescope. I'll show you a bit more about what those look like in detail in a second. But there is one other element, a headquarters. And because it's on two continents, the headquarters didn't have to be on either of them. And after much work and contribution from our government, from the STFC, they've been very generous and positive in encouraging and funding this project. We now have the International Square Kilometre Array, SKA headquarters, which is at Jodrell Bank. And this is a picture of the building, which was opened in July this year. There are 10 international consortia who are getting together to actually build the telescope. And the UK is leading in two of these consortia, so the Synchronization and Data Transport, which is the one I belong to, and the Signal and Data Processing. And as I say, the UK has already committed 100 million euros, actually, I've said pounds, but I think it's euros, towards building the telescope, which sounds like a lot, but actually in terms of fighter aircraft and things, not that much. So these are the 13 member countries. The blue ones are the paying members, and the pink ones are the African partner countries. They're countries who really don't have enough GDP to be contributing to this telescope, but we want to build the telescope up through Africa in a sort of arc, right, going like that. So up through Namibia, Botswana, Zambia, Zimbabwe, up to Kenya, Ghana, and out to Madagascar, Mauritius. And equally in Australia, it wants to go right across Australia. So that's why we need the African partner countries. The other thing is interesting to notice is that the United States are not members. This is because they decided that they wanted to build their own high-frequency network of telescopes, which they will do somewhere about here. And that will actually complement what we're doing quite well. But it does mean we don't get American funding. Right, now I must give you a formal specification. I'd be failing in my duty if I didn't. So the SKA will be a large radio telescope for transformational science, which is what gets you funded. It's going to have eventually 1 million, the whole point is the square kilometre, it's going to be 1 million square metres collecting area. And I say eventually, advisedly, what is being built now is 10%. It's in 2 stages, a 10% and then the full thing. It will eventually have huge baselines. These little dishes will be spread out over about 3,000 kilometres by the time they get up to Ghana. But the first stage is just in South Africa. It will be what's known as a wide field interferometer, which means it has a lot of field of view at any given time, which is really excellent for looking at lots of things at a time and doing big surveys. It will range in frequency from 50 megahertz in Australia to 15 gigahertz and possibly eventually more in South Africa. And there will be aperture arrays and dishes. I'll show you pictures of those in a minute. Once you've got your receptors, the signals have to go to a high-performance correlator to put the signals all together in phase, as I showed you. Then the signals have to go to basically big computers to make the digital signals into images, because although we're good at taking digital data, we really do like to respond to images. So that's the HPC science data processors, high-performance computers. And to do this, we need an optical fiber network, which is quite complex, and the thing that we've been looking at individually. As I said, 2 phases, 10%. The first 10% is going to cost 675 million euros. And I am a little frightened by that number because the idea originally was to have a much cheaper array. And I'm slightly worried that this will get built and the whole thing will never get built, but hopefully we'll see. Depends on the other pressures on the world and the world's finance. It will have a huge increase in survey speed, so we'll be able to look at lots and lots of things very quickly. And as I've said, it's on 2 continents. Right, let's look at the details of, oh, sorry, I should have just pointed out that this plot is a plot of sensitivity of radio telescopes against date, and the SKA, which hopefully is actually slightly falling off this date now, but is just a natural continuation of the improvement of our sensitivity. Right, what will it actually be? Well, it will initially be 133 15-metre dishes in South Africa in phase 1. And they'll look like this one, not this one, that's an older design. They'll look like this one with the radiation coming into the primary, secondary, and then going into the first bit of the receivers there. Phase 2 will see 2,500 of these dishes spread out across Africa, hopefully. Now the South Africans, as I said, had already built a precursor telescope. It was called Meerkat, and it consists of 64 dishes that look like that. And that's not an artist's conception. That's a photograph of the first real dish. And isn't it gorgeous? So they have already started making stunning observations of the galactic center. They're really doing a really excellent job, and it's a great credit to the engineering skills of South Africa, which, you know, a decade or so ago were almost non-existent. So they really have pulled themselves up by their bootstraps. Right, so those are the dishes. That's the higher frequencies in South Africa. The lower frequencies will be done by something that looks like that. So that's 131,000 log periodic antennas in Australia. They look like wire Christmas trees or perhaps television aerials. And for longer wavelengths, so they're talking about, you know, these sort of wavelengths, you don't need the complication and the expense of the bent metal involved in making a beautiful dish. It's just as effective to use these things, and you can make lots more of them. So eventually, in phase 2, we're hoping to have 1 million of these spread out across the desert. They are arranged in groups called cores, and then there will be little stations all around, but further away. That's the hardware, and in a couple of weeks' time I'm going to go to the next engineering meeting to find if that's all been approved. We hope it has. But apart from that, it has been a huge diplomatic effort to coordinate the desires and aspirations of these 10 different countries around the world. And so what's come about eventually, after lots and lots of shuttling to and fro, is that the Square Kilometre Array organisation is going to become an intergovernmental organisation, which means it's going to become like CERN, basically. The treaty to make it an IGO was signed in Rome in March this year. It's still waiting to be ratified by all the countries' governments, but it's rather essential for a very practical reason, in that if you're an intergovernmental organisation, you don't pay tax in the country you're in. So it makes it possible to build it without it going over the top of the budget. So that was a really important step forward. Right, so where are we at the moment? Well, my consortium, the Signal and Data Transport Consortium, passed their critical design review. It's an engineering processes go through beginning design reviews, and then when you get to your critical design review, that's supposed to be the end, the final thing, and then you go and build it. We had our critical design review in May last year, and clearly, because it's such a long time before the end, you know, things are going to change, so we are going to have to do some more work. However, the other consortium, the Signal and Data Processing Consortium, they've also passed their critical design review, and most of the other groups of people, there was a consortium to build the dishes, a consortium to look at the computers of various types, they've all passed their reviews. So now the final one we're waiting for is the system critical design review, so that's the whole thing, and that's happening in December. And it is hoped, if all goes well, that construction will start in the first quarter of 2021. And it's going to take about 7 years to complete, but hopefully the first science will be possible before then. This is the formal part I've talked you through now. Now I'd now like to move on to the part where I've had a bit more involvement, first as project manager and now as domain specialist, and also a few reflections on the process that we've been through. It's been very interesting being involved in this process. It's a very new thing for astronomy. Astronomers are scientists, and therefore great at having wonderful ideas and trying out prototypes and that sort of thing. And they continually want to push the boundaries. That's what we want them to do. That's what they're there for, to have the inspiration and the insight. Say, oh, couldn't we just do that? Or what about that? Or there's a spectral line there, or whatever it is. But it means if you're trying to convert this into an engineering project, you suffer from mission creep terribly. And we have. Originally, it was thought that this would be built by 2010, and you see here we are talking about 2021. So the engineers and astronomers needed to work together. They needed to learn to work together to translate the astronomical ambitions and needs into formal requirements. And that was done through a process of system engineering, which some of you may be familiar with. It's just a way of systematizing such a thing. The trouble is, this isn't standardized. It's not like building a bridge or a car production line or an underground railway or something. And it is changing all the time. So it's been quite a difficult process. The formal requirements now have been provided and have led to the design, but still, as I say, with this temptation to keep tweaking it a bit. The designs will then, next year, after it's been approved, be put out to tender. As I said, universities are great at one-offs. We're absolutely useless at producing 100 of exactly the same thing. So it goes out to contractors, and they will do the construction work. And then the astronomers will come, and the engineers will come back in to do the commissioning, to make sure it works properly. And then it will be a job for engineers to maintain and astronomers to use, probably remotely. And the job has been to coordinate this across the world while constraining costs. And only been partially successful, I think. Right, so now to come to the bit that I've actually been involved with. This is the Signal and Data Transport Consortium. We have two jobs. Our first job is to get the timing signals to the receptors very, very accurately. If you don't add all the signals together from all those dishes absolutely in phase, you won't get your astronomy. So that's a very important first job and close to my heart. And then the other job is to get the data from the receptors, from the dishes or the Christmas trees, to the computers. It's no good if it trickles into the desert sand. So first of all, to show you what's involved with getting the data, I hope this is going to work. Yes, here we go. Okay, data from the dishes and the arrays, 90 gigabits and 10 gigabits, coming from lots of different dishes and arrays. Total data rate of 23,000 gigabits. This is the central signal processor. Deals with pictures, images, streams of time strings, and then it goes to the correlator. From the correlator, it goes to the high-performance computer. That's somewhere probably about 900 kilometers away in Cape Town or Perth, and that's our job to do that. The science data processor is what produces the pretty pictures. It then goes to the archive, where the petabytes are rolling up at the rate of knots. And then, of course, that has to go out to astronomers across the world. And it goes out on these 100 gigabit per second fibers, basically, all over the world. So, coming now to the time and frequency reference, that's the bit I'm particularly involved with now. These are the requirements that the phase coherence of the array, and what that means is this adding together of the signals, is accurate to the equivalent of 1 picosecond between any of the signals that are added together. 1 picosecond. That's quite accurate. And for the timing, for long-term timing for pulsars, we're going to observe pulsars over a 10-year time baseline. And we want to know small changes that happen in their frequency over that time. The timing will be need to be good to 10 nanoseconds. So really quite stringent requirements there. We have a clock. We'll have a central clock, which is going to make an SKA timescale. This is a design done with NPL in Teddington, National Physical Laboratories. It's going to be made out of 3 hydrogen masers. So we've got 3, so when one goes wrong, we can see which of the others, you can triangulate between them. The timescale is going to become part of UTC. UTC is, that's the universal time, is coordinated from Paris, and it's a whole lot of clocks added together and taken an average of, and we're going to become part of that system. And then the transfer of an accurate frequency is going to be done by this sort of mechanism here, which has an active go and return correction, so that any frequency you send out is corrected across all the telescopes all the time. So that's been the challenge. That's been the challenges for the data and the challenges for the time and frequency distribution. And these, of course, all have to go over optical fibers. Infrastructure is actually the most expensive part of what we do. This is what it looks like rolling out fibre across the Australian outback. You can see two little telescopes there, and there's the fibre quite literally being rolled out. And of course, so that's in Australia. The desert in South Africa, of course, is also equally full of fibre. So it's got cables and trenches and ducts and manholes and draw pits and all sorts of things. This is our leader of our consortium, looking down one of these manholes to see the fibre all rolled up down there. It's all underground, buried in the core of the telescope. But when you're going over these really large distances where there isn't a fibre existing, it's quite expensive. So outside the core, the fibres are going to be carried on the power lines, the power network, which surprisingly in South Africa is quite a well-established power network. So in the core, the telescopes are close together and we need to bury it to stop interference, but further away it can go overhead. So this is a loop of fibre waiting to be put overhead on the power lines. And looking up in South Africa, you tend to see other interesting things. That, I don't know if you can see the telegraph wires going out there and there. That's a telegraph pole with a social weaver bird colony built onto it, which is very interesting. That can be a bit of a nuisance if they start doing it on your telescope. But just a reminder that it is actually still quite remote. And this is the processing building in the Karoo. So when the signals come from all the little telescopes, they come into this building here. They all come from behind this mountain that the picture's taken from, that I'm standing on. And that's used, again, to shelter for interference, because there are high-speed computers in that building and we don't want them interfering with the signals. Also, this building is mostly underground, which is why it looks sort of low and insignificant, again, to shield it. This building here is where the dish construction hangar. Right, so that's given you a sort of overview of what's there and what's going to be there. Now let's move on and think what it's going to do. Once we've got these gorgeous photons, and they are photons, they're radio photons, but they are photons, what are we going to do with it? Well, I'm sure lots of you have seen this picture before. It's, of course, a cartoon history of our universe, the standard model, working from the Big Bang on the left to today on the right. This area here is where the cosmic microwave background radiation comes from, and that's not going to be what we can do anything with the square kilometre array. That's the province of satellites like Planck and WMAP. But once the universe turns on after the dark ages, when all the hydrogen is getting together and beginning to form stars, once the first stars turn on, what's called this epoch of reionization, everything to the right of that is fair game as far as the SKA is concerned. So it'll be everything from the earliest stars, the epoch of reionization, what's happening to the hydrogen there, how the stars form, galaxies form, planets form, how the galaxy clusters form, etc., etc., etc. All the structure that we're seeing in the universe today. So going over that in more detail, this is a little cartoon of the epoch of reionization. So what it is there is the stars start to burn on nuclear fusion, and they begin to ionize the hydrogen around them, and they produce little bubbles in the hydrogen around them, and then spread and spread and spread until all the bubbles join together and the whole of the hydrogen cloud is ionized. That produces very characteristic structure in the integration observation along the line of sight, and we're hoping to detect that. It's this same 21 centimetre line that I was talking about before, but that will be observed from right back in the beginning of the universe. But we're also hoping to be able to make pictures. This is a simulation of what we think it may look like as the hydrogen gets ionized round the stars. You can see the birth of the first stars and then beginning to get bigger and bigger and bigger galaxies, etc., etc. And we will also be looking at pulsars. We're hoping to find all the pulsars in the Milky Way. There we are. Right, so we're flying now through the Milky Way, looking at pulsars. All these little spinny things are pulsars flying up above the Earth. So they're all neutron stars spinning and giving out beams of rotation. We're hoping to find at least 30,000 of these, probably lots and lots, several thousand millisecond pulsars, and the first ones in the galactic center, possibly the first, oh, here we are flying up right over the top of it. And you see how many we expect there to be in the galaxy. There are going to be a lot of these. And this is going to give us a wonderful network, a huge timing network, because that's what we use pulsars for mainly, very accurate clocks. This is going to give us a huge timing network of very stable clocks. So we hope it's going to give us tests of general relativity and gravitational waves. You know, we've already found gravitational waves from merging black holes, pairs of black holes or pairs of neutron stars, but we need to see much bigger waves, much longer wavelength waves, because there should be gravitational waves right from the Big Bang. We should be able to see those, but we need a much bigger detector. We need this detector that's the size of the galaxy. So when these huge waves come through the galaxy, they make the clocks move and we can detect that. So that's going to be a very exciting piece of work to do there. We're going to be looking at lots of individual galaxies, just an example of a really rather nice one there. But we're also going to be doing these very big surveys of galaxies, as I was saying, this 1 billion galaxy survey in 3 dimensions, because we'll have redshifts for them and also spatial distribution. So this is going to show us a lot about the distribution of matter, including dark matter, and possibly also dark energy in the universe. So we'll be able to ask questions about dark matter and dark energy, and also questions about general relativity. Coming much closer to home now, we shall also be able to look at forming planetary systems. What do planets look like as they form around other stars? We now know that almost every other star we look at has a planetary system, but we want to catch them in the act. This is a picture. This is actually data from the ALMA telescope, which was the first telescope to be able to do this. We shall be able to do this for many, many more examples. You can see that the fact that it's splitting up into rings is where little conglomerations of matter are sweeping out clear rings as they turn into planets round the star. And the bottom, of course, is an artist's impression of what it should look like. We can do other things as well, hopefully, so-called astrobiology. We can detect a lot of emission and absorption lines of amino acids and other complex hydrocarbons, the sort of molecules you need to form life. They seem to be out there. The universe seems to be pretty well seeded with them. So that will be interesting to look at the clouds and the nebulae where those are found. We can also, if we feel so inclined, start asking questions about searching for extraterrestrial intelligence. We can search much more widely than we can at the moment. So at the moment, the current searches are confined to just the few stars within that little circle there. But we should be able to cover all the stars contained in that big circle, and therefore have much more probability of finding something, should there be something there to find. Finding signs of life, very simple life on other planets, I think has much more chance of succeeding rapidly, but the possibilities are also there. And fast radio bursts. The unknown, something we don't understand at all at the moment, but now we've got the ability to detect signals very quickly because we're more sensitive. We can now see that the universe is flashing off. Things are bursting out all over the place all the time. It's very dynamic. Stars and black holes colliding, huge flashes of energy being emitted. We don't know what we'll find. We will almost certainly find something that we haven't predicted. Looking in different regions of parameter space almost always gives you a new discovery. So we are hoping very much for new discoveries, enlarging our knowledge of how marvelous this universe we live in is incredible creation. And of course, depending on how you look at it, you can regard it as each new discovery adding to God's glory. So now coming to put the science and faith together, putting these two complementary worldviews together. How do we think about these discoveries in the light of faith? The emerging picture, as you will see, is quite unlike the 4,000-year-old picture I showed you at the beginning, not surprisingly, apart from the fact that both did have a beginning. But the universe seems to be a place of ongoing creation, a very dynamic place. And it seems to me that there's only an issue if you find it necessary to read the Bible or other books of faith literally as a textbook. It seems to me that God cannot in any way be less than his creation. And so science, which is our knowledge, our activity in the universe so far, sort of occupies a small bubble within this total area of knowledge that belongs to everything that there is. So we can only explore what has been done within our knowledge. We can't prove or disprove anything outside that. And as God, by definition, has to be other than what we're already looking at, it seems to me it's not asking the right question of science to say, can science prove or disprove God? It just doesn't make sense. There is actually a mathematical theorem, the Gödel's second incompleteness theorem, which says if you have a closed system, you need information from the outside to talk about it properly. And it seems to me that that's a good analogy for our sphere of knowledge. But we do know that there's something. We know there's something where there might have been nothing at all. There's no really obvious reason why there should be anything. We also know that the universe operates according to laws and processes, and they seem to be ordered and rational, which is just as well for us, because we wouldn't be able to do science at all if Newton's law changed every time we stepped out of bed. It would be very disconcerting. We can understand these laws, and that to me is stunning, that I can stand here and be talking to you about colliding black holes or the Big Bang or cosmic microwave background across the universe. It seems to me to suggest that our minds are perhaps not just destined to contemplate what's in this little sphere under this little bowl. And all these things seem to me to be consistent with being led to understand what God has actually done. We have the evidence in the Word and the works, I think. Why not both? These scientific processes appear to be God's normal way of working in creation. Science is revealing what God has done. And who are we to criticize and refuse to accept it? As Galileo said, how the Bible teaches how to go to heaven, not how the heavens go. And ultimately, science enables us to explore these wonderful things that God has done. It's an extraordinary universe, but we are far from understanding it all. We need to stay very humble. We are just at the beginning. What about those 11 dimensions and all the multiverse and the dark energy and everything else? We are just at the beginning. And maybe at some point when our knowledge expands to the state of God's knowledge, we will understand everything. But now I know in part, then I shall fully know, even as I am fully known. Thank you.
Fascinating. Thank you ever so much for that. We've got plenty of time for some questions. Now look around to who might be the first one to ask one. I know, but there'll be a microphone. I think Steph's coming with a microphone, so you want to hold on until it gets to you.
Thank you very much for that illuminating presentation. But just at a very practical level, is there an issue, given the preciseness of timing and space that you're encountering or planning to encounter, say particularly across Africa, is there an issue relating to the stability of the Earth? The Earth's crust itself, does that not potentially move and therefore potentially distort things?
Good point. I mean, we do think about earthquakes. Unfortunately, we can't predict it. I mean, there's not a routine way we can predict earthquakes. I mean, I think each one will have to be coped with it on its own basis. I mean, in principle, we're in a low earthquake area in both cases, so hopefully that won't be too bad. But it's a very good question, and you know, if there is, I mean, it's something that's of concern, of course, for the structure of the telescope as well. We certainly want to be able to withstand anything that the crust is going to throw at us. But yes, there will, you know, if there is a significant earthquake, it certainly will cause glitches, and they will have to be dealt with, corrected, or the data just dropped for that point, you know, for that part of the time.
Further forward, thank you, Steph.
Hello, wanted to talk about any security risks you might have considered in relation to both the installations and the data that you're collecting. Are there any? What are they? Are you happy to talk about them? What steps have been put in place? And can you speculate about the motivations of people who may want to prevent you from discovering more about the work of God?
Wow, lots of questions there. Security, yes, of course. Start with Africa. Yes, we're in the middle of a continent which is still majorly poor, and we are putting, fortunately not copper much, above ground, but still, yes, there's a lot of stuff that people might like to steal. The Karoo is fairly unpopulated, though it's actually surprising how many people there are there. The measures that are being taken place are obviously just initially the first physical ones, you know, the usual difficulty, you know, we will make it difficult to get at the telescopes. In Australia, it's a little bit different. Basically, Australia is not quite so poor, and there aren't very many people in the area where the telescope is in Australia. There are a lot of sheep, but really not very many people. There are about 100 people in the whole area of where the telescope will be. So the actual physical risk is probably less there. The sort of data risk, it's an interesting question, this one. The data, of course, are just noise. So anybody stealing them is going to have an awfully disappointing time. They're not going to know what to do with them much. But that doesn't mean to say that somebody in his bedroom, you know, in his attic in Slough might fancy making the telescopes dance to his command. So yes, we are thinking quite seriously about putting in the same sort of security that commercial networks have. So yes, there is a whole area in the SKA building that I showed you working on that at the moment. The motives, well, apart from just sheer interference to prove they can, you know, I don't think there's much profitable stuff they can get out of it. It's not as if it's real information. It's not bank accounts or anything like that. So I think the motivation really will be just awkwardness.
Forward one, then there's a question here as well.
Thank you very much. Two very, very brief things. In what you're observing through all these telescopes and things like that, is everything getting simpler or more complex? And the other question is, what is going to be the impact of 5G as it's rolled out?
Right. Are things getting simpler or more complex? I mean, I think things are getting more complex in that we're discovering more and more things, like those fast bursts that I showed you. You know, we've no idea what they are at the moment, but they're coming from all over the sky, so they have to be celestial, they're not terrestrial. And getting more complex in terms of just a much bigger quantity of data. I mean, I did give you some indication of the quantity of data. It's of course, technology is rushing towards us, so it's getting less and less frightening, but it still is a big amount of data to deal with. So I think things are getting more complex. 5G. Wow, I don't know. I'm a beekeeper, and I've been told 5G is going to affect my bees, but I don't know how it's going to affect the telescope.
Much shorter wavelengths.
Yes, Do you know what the wavelengths are?
Very short.
Very short. Hopefully they will be, I mean, that 21 centimetre line is supposed to be a world protected band. I mean, it's being encroached on from all sides, but hopefully they will keep it protected. So hopefully we'll still have that. But yes, I mean, it will, the band, I mean, fortunately the bands are well defined and you just can't observe there because it just drowns you out.
Thank you. I think the next question was just here.
Thank you very much. These two telescopes, will they work like the two LIGO installations work and check up on each other, or is it just to build one big aperture? And if you're building a big aperture, can you build it the width of the Earth's orbit? Take a reading summer and then in winter and add them together.
Right. The telescope, the South African and the Australian telescopes are operating at different wave bands, and they're looking, therefore, at different things most of the time. So, sorry, excuse me. I'm sure at some point, some bright spark will say, can't we use the whole lot? But at the moment, the programs that are planned are separate. Using it as a big telescope from the Earth's orbit, I mean, we will by definition do that because there's nothing else we can do. We'll be we'll be taken round willy-nilly. But so yes, I mean, things will be observed differently at different times of the year. So yes, that will happen. But I think there's no plan for the two to operate together as a unit at the moment.
And then one question just behind you, Steph. Yep, gentleman there.
That was fascinating. You spoke about mission creep on the one hand and very precise timing on the other. Does that imply the dishes of your bowls and your Christmas trees are frozen for all time and it's only a matter of building more of them across Africa? Or is there the prospect that you could have modified designs as the decades go on?
I'm sure the designs, if we do get to building the right across Africa stage, I'm sure the designs will be modified. I just can't see anybody being willing to leave them alone. And yes, you know, technology moves on, we get different ideas, things are different. So I expect it will move on. I don't think it'll be so much the dish design. It is somewhat new, but it's probably going to get put out around Africa fairly soon if it does get put out. So I'm not sure it'll be so much that. Certainly the problem of doing the frequency transfer across Africa is not yet completely solved. So we will have to think a bit harder about how we do that. And I'm absolutely certain people will think of better ways to do things in the next couple of decades when the big complete design is finished.
I think there's a question down closer to the front here.
Hello, thanks for a very fascinating talk. You've obviously chosen the locations of the telescope very carefully to avoid interference. And I think it was yesterday I saw in the papers that SpaceX are planning to put 40,000 satellites into orbit to do internet services. Just wondered if you think you're going to have problems with things getting in the way of the signals coming through.
Absolutely. If they do that, I mean, it's just going to be horrendous. There's enough problem already with satellites going over. I mean, fortunately, you know where satellites are. So you say, that's Joe Blogg's satellite coming over, and it just wipes out your data for that little bit of time. But, if they're going to put whole constellations of satellites out there. It's, eventually we'll end up on the back of the moon. That'll be the only place to do it. But not quite there yet.
And there's a question just behind you, Steph.
Yeah, thank you for your talk. Very interesting. I just had a question about some of the partner countries in Africa. So essentially, when you're putting this infrastructure, you're creating a backbone network. And I just wonder if there's any, do they get any benefit from this, or is this data just for the telescope?
Well, I'd cut out of my talk one of my slides, which shows the nearest little town to where the telescope's being built in South Africa is called Carnarvon. Carnarvon, I can tell you, used to be a complete dump. There was drug problems, there was alcoholism, there was no unemployment. It was awful. Now they have got their fibres to their school and their hospital and the library and the internet. They have got their local brick builder has been taught how to build world standard bricks, and now has a whole group of people working with him, and he can't turn them out fast enough. There's the hotel keeper has had to buy up several new buildings, and the town is booming. So yes, I think this is going to be welcome wherever it goes in Africa, because it's just bringing infrastructure with it, and you know, that just helps. So we're very welcome at the moment.
Can I ask one ultimate question? As to what do you think this is going to tell us about God? To come back to
that he's even more wonderful than we imagined. Yes, the universe is a fabulous place.
Great. Thank you very much. Can you join me in thanking for Althea for a fascinating